Hello class, this is Mr. Krieger. I'm doing the next lesson. I just want you to know that this lesson is for my class. My class is with Ms. Stillman, Mrs. Stillman's class, and Mrs. Berthel's class. So we want to welcome the students from Ms. Berthel's class. So this is Unit 8, Part 2, Lesson Number 1. You should have a copy of that. It should have been emailed to you. You should have it somehow. So make sure you have a copy so you take notes. The lesson is proving triangles are similar, okay? So this is the lesson. All right. What happens when diagrams are scaled? What do we know about their angle measures? We know that angle measures are preserved. Let me get another pen. Okay, and what do we know about the sides? The sides remain, that's not good either, in proportion. Okay, so let's remember that there's a sequence of these things that will cause one figure to completely coincide with a congruent figure. You should know that that is a sequence of rigid motions. Therefore, when we dilate a figure and then perform any sequence of rigid motions on the dilated figure, the final image must be similar to the original pre-dilated image. So here's an example of what's going on. We know that this triangle is similar to this triangle. Now we're going to take a look at a sequence of similarity transformations, not specifically, but just what you would need to do. First of all, with the original diagram, the pre-image, it's much smaller than maybe not much smaller, but smaller than the image. So if we dilate it to be the correct size, now it's the right size, but it's still not on top of the image. So then we'd have to follow a sequence of rigid motions to make sure this triangle aligns with that. So similarity transformations is a combination of a dilation with your rigid motions. Okay? How do we know when two triangles are similar? Three pairs of corresponding angles are going to be congruent. So the angles have to be congruent, and the three pairs of corresponding sides are in proportion. They're not going to be congruent because the triangles are not the same size, but the sides will be in proportion. We'll take a look at that in a minute. Okay? Do we need to know about all 6 parts of the two triangles to prove that they are similar? You should know that just like in congruence, when we try to prove triangles congruent, for similar triangles we have shortcuts. So there will be shortcuts. I'll say there are shortcuts. And we're going to look at those next. Okay, it's the next page. So you can go take a look. All right. Oh, bled through. All right. So, in fact, let me put something in between here so it won't bleed through on there. All right, so first similarity shortcut. Angle-angle similarity theorem. When two angles of one triangle are congruent to two angles of another triangle, the triangles are similar. So let me show you what that means. Suppose we have two triangles. We'll name one ABC and the other one DEF. All we need, at a minimum, is that two angles, one angle from each of these and another angle from each of these, are congruent to each other, and we will know that these triangles are similar even if we don't know anything else about the triangles. As long as two angles from one are congruent to two angles from the other, then we know the triangles are similar. Triangle ABC is similar to triangle DEF, and we would say that the triangles are similar by angle-angle similarity. Okay? Second shortcut, side-angle-side similarity theorem. If two sides of one triangle are proportional to two sides of another triangle, and their included angles are congruent, then the triangles are similar. So here's the example. So let me name this triangle ABC and DEF. And let me make some measurements. Well, first, before I do that, let's say angle A is congruent to angle D. Let's say AB is 2 units and DE is 4 units. Let's say AC is 3 units and DF is 6 units. We will be able to prove that these triangles are similar by side angle side similarity. We got the included angle, the angle between the two sides, and then we've got to check to see if the sides are in proportion. I think you can clearly see that from these numbers. We made the numbers easy on purpose, but here's how you would check it if it was more complicated. You would match up AB to DE, and you would match up AC to DF, and if these ratios are equal, the triangles will be similar by side angle side similarity. So let's put these numbers in. AB is 2, DE is 4, AC is 3, DF is 6. These both reduce to 1/2, so the sides are in proportion. The included angles are equal, so we can say that the triangles, I'll put it here, triangle ABC is similar to triangle DEF by side angle side, or SAS, similarity. Okay, so that's the second shortcut. Third shortcut, side, side. Oh, actually, before I do that, let me just show you something. This is what you cannot do. Let me go to this diagram right here. Now, if you take a look at the information on these triangles, these angles are equal. This side is double this, and this side is double this. But these triangles are not similar because the angle is not between the two given sides. Just like for congruent triangles, you can't use side-side angle congruence, and you can't use side-side angle similarity. So this will not work. Okay, so let's go back. I'm actually going to use this so it doesn't bleed through. Let's go back to our third inequality postulate. I'm sorry, the third similarity theorem. If three sides of one triangle are proportional to the three sides of the other triangle, the triangles are similar. So let's take a look again. We'll call this triangle ABC. We'll call this triangle DEF. We'll call this side 8, 10, and 6. We'll call this 12, 15, and 9. And what we want to do is we want to see if all the sides are in proportion. So we're going to make our ratios now. And it doesn't really matter image or pre-image. You just want to make sure the ratios are consistent. Like, for example, AB has to be matched to DE. AC has to be matched to DF. And BC has to be matched to EF. If these are all equal ratios, then the triangles will be similar by side, side, side similarity. Let's check. AB is 8, DE is 12. AC is 10, DF is 15. BC is 6, EF is 9. Let's see, this is 2/3, 2/3, 2/3. They're all equal. Therefore, these triangles are similar by side, side, side similarity. Again, I could write out triangle ABC is similar to triangle DEF, but this would be the reason. All right, now we've seen the shortcuts. Let's practice a little bit. Okay, so determine if the following triangles are similar, and if they are, state the similarity theorem. So again, pause the video, see if you could figure this out. I'm going to do it right now, but you could try it yourself. This should be similar by side, 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 but not because there are numbers on every side, but because the ratios are true. We could set up the ratios like we've done in the past. Let me just take a look how I did it here. I just want to find, I just made the ratios. Like, for example, I know this 4 matches to this 20. This side is the corresponding side to this side, 4/20. 2 matches to the 10, and 5 matches to the 25. If these are all equal, these triangles will be similar by side, side, side. This reduces to 1/5, this to 1/5, this to 1/5. They're all equal. These triangles are similar by side, side, side similarity. Now you could try problem number 2. I think if you see it's very, very clear. You got these angles are 38, these angles are 70. These triangles are similar by angle-angle similarity. And the last one, if they are similar, it's going to be side angle side similarity, but we've got to check those ratios. Is 2:3 the same as 6:9? Well, 6/9 does reduce to 2/3, so it is in fact true. So these are similar by side angle side similarity. Now we got a harder question. Now, these triangles could be similar by side, side, side similarity, but I don't even know which sides match up to which. So I'm going to help you set up the ratios, and then I'd like you to try to see if it's true. So let's see. What I'm going to do is I'm going to take the names of these triangles, WXZ and XYZ, and I'm going to align them like this. This is what you want to do. Now, when we make our ratios, we are going to take like the first two letters, WX, and align it with XY. Those sides have to match. XZ has to match to YZ, and WZ has to match to XZ. Now, these have to be equal for the triangles to be similar. Please pause the video, plug the numbers in, and see for yourself if the triangles are in fact similar. I'm going to do it right now, but hopefully you've paused it and tried it. Let's plug in the numbers. WX is 15, XY is 12. I'm sorry, no, that's not true. XY is 10. Okay, oh, I think I'm more, yeah, well, whatever. All right, 15 to 10, XZ is 12, YZ is 8, and WZ is 18, and XZ is 12. Let's see if these are equal. 15 tenths is 3 halves, 12 eighths is 3 halves, 18 over 12 is 3 halves. These are equal, so this is similar by side, 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 similarity. All right, so that's how we check to see if triangles are similar. But I just wanted to mention, when we do proofs, which we're going to start right now, this is the primary reason we give in proofs for triangles being similar. So let's actually take a look at a proof. Before we actually do the proof, though, what I'd like you to do is I'd like to reintroduce the idea of an altitude to you. We've learned about what an altitude does, but we're going to just refresh. An altitude creates right angles. That's the special thing that an altitude does. So we're going to use that in this proof right now. Let's take a look at what we have. We have angle B is congruent to angle K. That's this and this. That's a given. I'm going to do my proof by bullet points. Angle B is congruent to angle K because of given. That's one angle. Now we're told that CD and LM are altitudes. And we know that's a given. Now we need to find another angle. We're going to get that other angle from the altitudes because we know altitudes create right angles. Now, I didn't mention this, but I'll point it out now. We want to prove that this triangle here is similar to this triangle here. In other words, triangle BDC, which is this purple one, and KML, which is this one. So far we have one angle in each of those triangles. Now we're going to have to find the second angle. Well, we know altitudes create right angles right here. So what we're going to say is angle BDC and angle KML are right angles. And you know the reason, because altitudes form right angles. Now we got our angle. Oh, we have to do one more thing. We got to say angle BDC is congruent to angle KML. You know the reason. All right angles are congruent. And now we can say that triangle BDC is similar to triangle KML because of, as this will always be the reason in the proofs, angle-angle similarity. Okay, make sure you do your homework.